oxidizing agent that we are going to use is acidified potassium permanganate or acidified potassium manganate 7. We know its concentration. The concentration is 0.02 m. We will use it to determine the concentration of our reducing agent, which is iron 2. So we are going to use iron 2, and we will determine the concentration of this solution. The process is called standardization. We are going to standardize this solution. And we have the conical flask. This one is where we are going to put our iron 2 sulfate solution. And we have the burette. We are going to put potassium manganate 7. We will react both of them. We will get the volume of acidified potassium permanganate from the burette. We will already know, we will fix the volume of iron 2 sulfate because we are going to pipette. And we are going to use 25 centimeters cubed pipette. And we will draw the solution and put it in the conical flask. And let us start. We have the 25 centimeters cubed of acidified iron 2 sulfate. It is going to be our reducing agent. We will put it in the conical flask where the reaction will take place between it and manganate 7. We put it there, and this redox reaction, it does not require the indicator because, as you can see, acidified potassium manganate 7 has got a very deep purple color. So when the reaction is over or when we reach the end point, this color will change. So we put our acidified potassium permanganate into the burette like that. And right now I remove the filter funnel because I don't want the solution to keep dripping inside the burette. And our burette reading is exactly 8 centimeters cubed. 8 centimeters cubed. And now I want us to react the two solutions. When you start titrating, you use the left hand side to open the tab of your burette, and then you shake your right hand side. That is if you are right-handed. Let us now start reacting. As you can see, the reaction is taking place because immediately when acidified potassium manganate 7 falls into the iron 2 sulfate, a reaction is taking place. You can see clearly that a reaction is taking place. So we expect at the end point, this colorless solution down here in the conical flask to change to purple. And that will be the characteristic of the end point. Oh, sorry. We have reached the end point, and let us now get, although I have moved very quickly near the end points, but I think we have not added so much excess. Let us now read the final burette reading. The final burette reading is exactly 20 centimeters cubed. So it is 20 centimeters cubed. And now our titer value, or our amount of potassium permanganate which have been reacted, is 20 centimeters cubed minus 8 centimeters cubed. So we have spent 12 centimeters cubed of acidified potassium manganate 7. That is what we are going to use to calculate the concentration of iron 2 sulfate solution. So that is the end of the titration. When in our titration, we titrated, or rather, in the experiment, we pipetted 25 centimeters cubed of iron 2 sulfate, and or rather of iron 2 ions, and we put them in this conical flask to react it with manganate 7. And the concentration of iron 2 is unknown because it is the one that we want to determine. The volume of manganate 7, we got it from the burette, and we had the initial burette reading was 8 centimeters cubed, 8.0 centimeters cubed, and the final burette reading was 20.0 centimeters cubed. If you subtract our volume that has reacted with iron 2 becomes 12 centimeters, 12.0 centimeters cubed. The concentration of manganate 7 we prepared was 0.02. Now, how do we calculate the concentration of iron 2? One, we want first of all to write the chemical equation between manganate ions and iron 2 ions, and we have them reacting manganate ions plus iron 2 ions, and remember it's acidified. We are going to get, okay, manganate 7 is a strong oxidizing agent. It is purple. It oxidizes iron 2 to iron 3. So one of the product is iron 3. Then we expect, because we have hydrogen ions and we have oxygen, we will also form water. And finally, manganate 7 will be reduced to colorless manganese 2. So we have manganese 2 ions in aqueous form. If we balance this reaction, we put 5 there because of the number of electrons which are lost and being received by manganate 7. So here it is 5, and the manganate, the manganese is balanced on both sides. What hydrogen ions, or rather hydrogen on the left hand side is 1, on the right hand side is 2. Now we balance it like, okay, we multiply here by 2. Okay, oxygen. Let us first of all balance oxygen. Oxygen on the left hand side here is 4, and on the right hand side is 1. So we multiply water by 4 on the right hand side to make the number of oxygen on the right hand side to be 4. Now we we are left with hydrogen. On the right hand side, the number of hydrogen are 8. So we multiply hydrogen ions here by 8. So the equation is balanced, and we can see clearly that the ratio of the two ions which are reacting, the ratio is 1:5. This is what we call the mole ratio. Mole ratio. So it's the mole ratio that we are going to use to calculate the concentration of iron 2. And how are we going to do that? Since we have the volume of manganate and we have the concentration, we can know the number of moles of manganate which have reacted. We said you get the volume, which is 12, divide by 1000, this is centimeter cube, multiply by the molarity, which is 0.02. Those are the number of moles of manganate, the number of moles of manganate 7, which becomes 12 times 2, that is 24. Now we put in the decimals 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So those are the number of moles of the manganate ions in the solution that was, or rather the solution that we titrated, that is 20 centimeters cubed. Remember, again, these were the number of moles carried or dissolved in the 20 centimeters cubed, which reacted with 25 centimeters cubed of iron 2 ions. We can now be able to calculate the number of moles of iron 2 ions because we have the mole ratio. And since the ratio is 1:2, that is, for every 1 mole of manganate requires 5 moles of iron 2, therefore 0.00024 moles of manganate will require that now times 5 number of moles of iron 2. These are the number of moles of iron 2. And if you react, if you multiply 24 times 5, I think that is 120. Then we count decimals, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Those are the number of moles of iron 2. It is now very easy to calculate the concentration of iron 2 in our solution, because we have seen that in 25 centimeters cubed, we have discovered that the number of moles of iron 2 was 0.0012 moles. Concentration is based per liter of solution, so we will extrapolate from there. We ask ourselves, suppose we had 1000 centimeters cubed of such a solution, how many moles would be there? So here we use simple proportions, that is 1000 centimeters cubed divided by 25 centimeter cube multiplied by 0.0012. And when we are quoting the number of moles per liter, you write it as a capital M, and this one becomes the answer becomes, we are talking of 0.0012 multiplied by 1000, then divide by 25, we get 0.048. So the concentration of iron 2, it becomes 0.048 m. that is the concentration of iron 2, and I believe we have done it well, and that is the answer for the standardization of iron 2 solution, and that is what we normally do. The next lesson on there will be another still lesson on redox titration, and next time we are going to titrate dichromate 6 with iron 2. Dichromate 6 is also an oxidizing agent, and I'm going to do it. We are going to do it together. Thank you for listening to me.